even though we're not at 4 o'clock right now, doors have closed, so I'm gonna make the executive decision that we can start, okay? So you go first.
Okay.
You're the first.
Today we're going to be talking about a method that we developed for NMEA 2000 fingerprinting. So really quick, I'll do some introductions. My name's Dean. This is Anissa. I am a PhD candidate at the University of Rhode Island, where I'm in the Cyber Physical Systems Lab. And I am a prior commercial mariner. I worked on ships for about 7 years in New York City. I went to the United States Merchant Marine Academy. I was there. I joined the cyber team, so I was at least aware of bits and bytes, nibbles. I think that was the joke. It was 2002 to 2006. So ESX was a thing for the first time. We did the NSA cyber defense exercise, and we were the ones that made the rule that you can't just restore from a snapshot. That was our main cybersecurity strategy: restore from snapshot. So. After that, I worked in defense contracting, where I ran classified information systems. And now I'm currently the Chief Information Security Officer at Dispel. We do secure remote access for industrial control systems. So that's my day job. And night job is URI. And night job is I'm a reservist with the United States Navy with U.S. Forces Korea as a IP officer. So I keep myself pretty busy sometimes.
I would say too busy.
Yeah, and personally. I'll pass it over for Anissa to introduce herself.
So my name is Anissa.
You see the joke.
Yeah.
It's supposed to be funny.
Yeah.
Yeah, there we go.
So can we get a laugh, please?
Yeah.
All right, this is my LinkedIn picture too, if anybody wants to add me. So my name is Anissa Elias. I am, like I said, from Rhode Island. I work for a now medium-sized company in maritime security called Right Solutions. Over there, I'm a software research engineer. I'm also a PhD candidate with Dean. I don't know if you mentioned that. We have recently become candidates, which is a big deal in PhD world. And I work with Dean at the Cypher Center at URI under the same advisor. And
Professor Yanson,
yeah.
who we have to thank for her support in this project and doing the research under the Office of Naval Research.
Yeah. So this research was supported by ONR, so the Office of Naval Research, under a grant that I think I have at the end. So we can shout them out at the end too. All right.
So James Campbell helped me on, and he's here in the front row, on a project that we did for DEF CON 29. Who was at DEF CON 29? Safe mode. A couple there. And what we called it was Open Bridge. And at the time, I was teaching as a lecturer at the United States Coast Guard Academy. And we had a problem where we wanted to teach about maritime industrial control protocols, but we only had like one trainer bus. If you went to the demo lab, it was like the same thing. Plug in, do your thing, unplug, go do something, plug in. So we wanted to address that problem because the same problems exist now as they did then, but we made Open Bridge project, and we really wanted to make learning about this protocol a little bit easier. It is based on CAN bus. We'll talk a little bit more about that. But yeah, our goals were to just make it more attainable, easier, cheaper, and kind of accelerate the learning process without needing to buy a boat, not needing to buy a GPS head unit. So really quickly, NMEA 2000 stands for the National Marine Electronics Association. They have a protocol, NMEA183, which is known as AIS, or it's known for AIS, but it's also used for lots of other things. And NMEA 2000 is used for bus protocol, bus communications on a ship. Let's see what else. It's based on the ISO 11783 standard. It is compatible with the SAE standard, which is cars. So you could, I guess, conceivably put your GPS head unit in your car and have them not overlap and fight each other. This is accomplished because it uses the CAN bus extended header to essentially derive a parameter group number. We'll talk more about that. A lot of our research, I'm not talking about that yet though. No, I'm going to talk about the research later. Yeah. You guys know that CAN bus uses two wires for CAN high, CAN low. It has a dominant and a recessive bit structure. It's pretty much leveled off by two resistors on the end. And this is going to get important later on. but really understanding that the CAN interface is kind of still the Wild West, as we've learned in Car Hacking Village and other places. It's not authenticated. It is built into almost everything. My excavator uses the same CAN protocol, same standard as NMEA2000. Again, I could probably put my GPS head unit in my excavator, right? So let's go to the next. This is kind of a default bus we pulled off the internet. You have to power the bus with 12 volts. Usually you'll have various different sensors along this lower line, which is a backbone. We talked about those two resistors on the terminator ends. And then everything on the bus talks and listens. We talked a little bit about that at our last demo, which we had unfortunately before this, so I couldn't promote it at the talk. But if you want to come back down to the Maritime Hacking Village, I'd be happy to revisit the demo and get you guys collecting some data on your computer so you can play around with it. We had ChatGPT, the GPTs, put together this drawing, which is horrendously not correct, of our actual test environment. So this is something you can go downstairs at the Maritime Hacking Village and see now. James is supposed to be guarding it. James is supposed to be guarding it. But it includes a wind sensor, weather station, AirMar, a Maritron head unit, and a Garmin chart plotter. I can't remember the model number. And then since DEF CON 29, really nothing has changed. Head units are still expensive. Like, you're not going to buy two of them and break one. Radars are still expensive. These sensors are hundreds and hundreds of dollars. So the problem still remains that there's not a lot of published research on this. There's not a lot of people that are spending a lot of time in the NMEA2000 world. There are a lot of leaders in the area that make training platforms, like Fathom 5 makes a great training platform. There's a couple, there's a training platform by Penn State down in the Maritime Hacking Village, but it's a one-time thing. And what we wanted to start, thinking about is how can we determine what's normal on a bus network like this? How can we determine what's normal so that we can then start determining what's abnormal later? Yep. And that's what Anissa is going to start talking about, the method that we developed to deterministically fingerprint NMEA2000 network. And then we can come back and talk about kind of what's next from that.
Yeah, for sure. And I just want to add on to the point. You can stand over there.
You want me to stand behind you?
So I can talk to you too. As academics, so Dean and I are both in a PhD program. So in academia, it's really difficult to do research on such an important topic if there's not a lot of open source data sets available for you to do research on. So I'm just going to introduce our system architecture generally. So like Dean said, what we had to first start with is data. So Dean, back when he was in the Coast Guard, actually set up the physical system, which consists of 3 devices and actually 5 nodes. And so what we started doing was took that physical system that actually cost a lot of money, I think. I don't know what the bomb is, but
James is watching it right now.
Yeah. And we have that physical system available to us at our lab. We hook it up to a interface device. So we use a logic analyzer. We use the Salier to collect CAN frames, to collect a lot of data to do our actual research on, to create a baseline of our system to then fingerprint and make open source or publicly available. So the biggest part that I'll be talking about is actually our software analysis stack. So that consists of a one database with multiple tables. We have databases for our system. So what the baseline known PGNs that are available out there. Actually, we talked about this in our workshop, but you can only access PGNs and what they mean if you kind of sign up for a NMEA specific, I don't know, how would you say?
You have to be a member of the association to get the standard.
Yeah.
And not every PGN is documented in the standard. So we were talking about this at the workshop, and we could collect PGNs that are proprietary PGNs, but proprietary PGNs are between the NMEA standard organization and the manufacturer. So if I made Dean depth sounders and say Dean head units, I could use the head unit to configure the depth sounder, to tell it how far it is away from the keel, or the DIN temperature sensor, or the DIN tank level flow meter, or whatever, right? So that could then put on the bus that information that another device could consume or do something with.
Yeah. But
right? The problem with that, I think, is that if you don't know what they are and they're running around in the bus, you could be reconfiguring without knowing it. The measurement for the depth under your keel could be a problem.
Yeah.
Rudder angle indicator could be a problem. When you have, boats that, running into bridges and into, the Suez Canal. So, so anyway.
Yeah, but also most important part is it's not available for people, right? You can't just go online and find it and do something for yourself. So what we wanted to do is get that and actually have it be publicly available for people to kind of search. If they get a PGN number, you go in and search and you can know more about whatever system that you're working with. We also have a table of PGN traffic, so frequency of the devices that are on our network, and then they all come together on our dashboard. We use everything to actually fingerprint our network, and we'll talk about that in a little bit. So if we go step by step, first thing we have to do is set up our physical system, set up our logic analyzer, and get the frame. So this is what a regular frame shot from a CAN bus would look like. There's CAN high, CAN low. Dean can talk more about it, but if time permits. You go from there, you take that CAN frame and you make it into a binary. So this is what a usual PGN binary looks like. So, or an NMEA2000 data frame in binary looks like. What we want is to extract the important parts, which make up our PGNs. And because I didn't have them on the slides, I wrote them down. R, PGN first. R is the reserve bit. DP is the data page bit. PDU or PD is the PDU field bit, and then PS is the PDU specific bit. Yes. And we take all of those and then we put it into a file or a pipeline that I made, and hopefully we'll publish as a library soon. And that will give you a PGN that you can then look up, and you can actually know what the frame message says. And similarly, we get the source address, which is just SA, which means source address, and that gives you information about the device transmitting that specific frame. And so Dean told me I have to put memes in this talk. So he doesn't know this meme, but this is very popular for younger folks on TikTok. But I was able to develop.
I don't.
He doesn't know any of the memes I put in here, but
never seen the show.
Yeah, it's really good. But,
it's about a cook, I think.
Yeah. So it is a very difficult process to go from like CAN frame to like an actual PGN that you know what the message says. So what I liked to kind of go over this process, I made a library that will go live hopefully on our GitHub page, OpenBridge, that takes CAN frames to binary bits to readable messages, and then we'll go over what that is right now. So once we get our CAN frame and once we get it into that looks something like this, the raw CAN frame, we are interested in the header. So the header is presented to us in hexadecimal format. We take that header, we get it into binary format. We then take what we decided was the important parts that make up a PGN, which is again, reserve bit, data page bit, PDU field bit, and PDU specific bit, and then that comprises of our PGNs. And so we clean up that binary combination. We bit flip the PS only if it's above 240. And then you get a PGN decimal that you can then go to our database that we made and actually know what that message says. And we do something very similar to source address. It's a lot simpler, but it's also included in the package or software stack that we made. And you get a source address, and that can be linked to the device that sent the specific PGN. And so all in all, in our database, what we really want to know, like the most important part of this is understanding the topological behavior of our physical system. So number one is we needed to get a device inventory database database that we got through the cane frames, through a very specific PGN, I believe 12699, if I'm not mistaken, and the source address. We take that, it gives us the information about what the device is. We can put that in our table or our device inventory database and get that. And then, second most important is where we get to the behavior of our network. So PGN frequency is something that we calculate whenever the devices are talking on the CAN bus. So we essentially just calculate the frequency of PGNs being sent from every device. We only calculate, obviously, unique PGNs, and then the if you have two devices sending the same PGNs, which happens pretty frequently, those PGNs linked to that device comprises of another unique PGN. So we have a PGN device combination. And we calculate the average frequency. That gives us insight into the behavior of our network and the behavior of our devices. And then lastly, we just get or have the PGN database that just comprises of every single PGN that was sent over our network for us as users to kind of know about. And so with all of that done, we actually made mathematical representations of things, which makes us feel like real academics too. So when fingerprinting a network, right? So why do we want to fingerprint a network, right? And Dean kind of touched up on this a little bit in the beginning, but there's really no way right now that's at least available to us where we can use to baseline a NMEA2000 network. So what we wanted to propose is a deterministic approach to this and create a deterministic fingerprint technique that, again, takes the topological information or the topological and behavioral knowledge of our network, because every network is going to be unique. Take those two, combine them, and then tell us when something is deviated from the baseline. And so what our equation variables are, what is the important parts, is the devices. Again, device inventory is really, really important. We have our set of devices that are known by the user, also known by whoever is going to be using what we have. We also have the set of known PGNs specifically sent by device D. So P of D is, again, let's say we have PGN1, device 1 and device 2 can send PGN1, but those sent by different devices will be added as unique PGNs. And then the average frequency of messages per minute at which device D will send PGN P of D. And that gets us to our actual fingerprinting equation, okay? And we have a real equation, which this guy didn't think I could do, but we got it done. And so we have our F, which is our deterministic fingerprint of the network. We have the important bits, which is D belongs to the set of devices bigger D, and then P belongs to the set of known PGNs, P of D, and then the expected frequency versus what we are getting right now. So the way we use this equation is you have the baseline. Every time a PGN is being sent, you take all of that information, you see what device is sending it, you ask, is it already on the network? You see if the PGN, is this a known PGN? Is this a PGN that is sent from a known device? Has this device ever sent it before? And then if this is all okay, has there been a frequency change? And that any of that happening will cause a alert to happen, and we can see it on the dashboard that we created. I don't know, can you see this? Yeah, I think you can see this pretty well. So I'm gonna play the video. I kind of have this set up, but so in our dashboard, we kind of just had the most important parts. So first is the physical representation. I just realized you can't see my mouse moving, but if you can point, Dean. So system map right here tells us what we actually know is on the system. So this is what our physical system looks like. Again, once you go downstairs, do give us a rating of how well ChatGPT did when it redrew our system. We have our device inventory right there. So again, we only have 3 known devices that we are okay with. We have PGN frequency, so average frequency of each PGN coming from specific device. And then at the bottom is our PGN monitoring, which is every PGN that we got from a run. Okay, so we have this, updates, we have a baseline. Let's say another run happens, okay? And let's say you did an analysis, just for the purposes of the demo, we're not gonna do this live, but we did an analysis of a new run, and there were a few bad things that came up when using our fingerprint. So what we developed here is it tells us the total of new PGN and device combinations. It tells us all new PGNs found, any frequency alerts, and any devices. So in unknown devices, most important. I don't think you want to have any device that you don't know on your network, because that is not good. And so if it's a new device, it gets added here. It also tells you what type of PGNs were sent from this specific device, and if you knew this, or if we've seen this PGN prior from a different device. We then get just a list of all new PGNs. Let me just speed through this. And then we get to what I like the most, which is frequency anomalies, right? So you get the PGN, source address, which tells you the device information, the current frequency that was measured, and then the baseline frequency, and we get a percentage of the difference to let us know that this is kind of bad, because it's above 85% for all of them. And then you get any new product information if you ask for it. And let me go. All right. Again, another meme Dean does not know, but he's been talking about this for so long. So I'm very happy that we are able to finally get the fingerprinting working and get the dashboard working. All in all, NMEA2000 is still very widely used. It's a very important protocol. There's no open source research about this, not a lot of available information about this. As people in maritime security, this is very important to us. So yeah, we finally were able to kind of propose something like this. Do you want to?
Yeah, and next steps are essentially we are talking about what is being said. We have the analog data to run a similar kind of analysis, machine learning on how it's being said. So we'll be doing analog analysis on the actual bit level. If you could imagine, if the characteristics electrically of a bus change, it will change the electrical characteristics of the zeros and ones. It was a huge amount of data. Like if the digital data is big, the analog data is like 200 times, no, 2,000 times it. It's a lot. So that's where we're moving to finish the baselining component of our research. We're then going to move on to a detect and protect. So detect being we've baselined, now we can find anomalies, and then eventually we're looking at methods to be able to essentially inline prevent bad packets, bad information from coming onto the bus. And we're excited to kind of move on to get through the kind of boring data. Like most of this is data processing, so thanks for bearing with us. But yeah, it's super interesting to be able to kind of finally have a deterministic method that will be able to say, hey, this network is now different. And you can compare networks between vessels that are supposed to be the same. So, I mean, if nothing else, a fleet could run this. It could be done inline, or it could be done in, batch type analysis where you just do the collection and do this offline. So with that, I think we have a couple minutes for questions. We can open up.
We have about 3 minutes before we're kicked out, so go for it.
Yeah. So AIS is generally going through an AIS transponder, which is could be on the NMEA2000 bus, right? So we're not focusing on that particular gateway, but I think James was just saying that he's very interested in looking at the gateway interfaces to NMEA2000, which could be a head unit, it could be a kind of radio that has an AIS interface. So for that, I'm not sure, but it would be very interesting. Anyone that is on the bus, anything that is on the bus could be doing a similar analysis, but that's a good idea. Yeah.
It's kind of like a drop-in system that you could install on board a vessel and actually get a fingerprint.
Yes, absolutely. Yep. That's the idea, is that initially it will be a passive listening device. Eventually it could be an inline device that actually can stop traffic and manipulate traffic in transit. I think we had another question in the back. Yeah.
Comes to the data rates on the bus. Has there been any suspicion, thoughts, work into the need for a covert comm? Was it already unauthenticated, unencrypted, nobody cares anyway?
So when I think about the bus, I think of it kind of like, public forum, right? Everything is there, everyone's kind of yelling, and the person that's yelling the loudest, right, the highest CAN prioritization in CAN arbitration gets heard, right? There are a number of attacks that do kind of like influence people's ability to talk on the bus, whether it's just flooding the bus or so on and so forth. I think what we're aiming to do ultimately is see if there can be an add-on that will enable the bus to have the capability to enable out-of-band communication and encryption. So that's the challenge that we're going to try to explore. We start talking about protecting. So doesn't exactly answer your question, but that's kind of where our thought is, because it is very difficult to, being that it's a public forum bus, everyone, gets a vote.
Wow.
We will be at the Maritime Hacking
Hacking
Village
Village, yep.
for the afternoon and tomorrow.
Yep.
So please come on down. We can do a little bit micro labs, but thank you guys all for coming.
Thank
We're
you so
flattered
much.
to see so
Yeah.
many people in this room. and
Definitely.
thank you.
Thank you guys.